In the vast expanse of the universe, where countless stars burn and billions of planets orbit, one question has captivated humanity for millennia. Are we alone? This profound question transcends borders and generations, inspiring scientists, philosophers, and dreamers alike. Today, with the most advanced technologies at our disposal, we are closer than ever to uncovering the answers. Each discovery, whether it's a distant exoplanet or an icy moon in our solar system, offers tantalizing clues about the possibilities of life beyond Earth. Consider the story of Barnard's star, a faint red dwarf quietly moving across the night sky. This unassuming star, located just 6 light-years from Earth, has intrigued astronomers for over a century due to its high proper motion, the fastest of any star relative to the Sun. For decades, Barnard's star seemed solitary and unremarkable, a cosmic bystander. But in recent years, it has revealed one of its secrets, a rocky planet known as Barnard B, orbiting close to its dim glow. This discovery, confirmed after decades of painstaking research, challenges our understanding of planetary systems around red dwarfs and expands the horizons of exoplanet science. Barnard B, however, is only one piece of a larger cosmic puzzle. Moving farther into the solar system, we find Ganymede, Jupiter's largest moon, and Europa, its icy sibling. Both moons are unique worlds with features that astonish and excite scientists. Ganymede, with its towering size and its magnetic field, holds secrets beneath its surface, a vast subsurface ocean potentially teeming with the conditions necessary for life. Europa, meanwhile, boasts towering geysers that erupt through cracks in its icy crust, hinting at a hidden ocean beneath, a reservoir that could hold twice the amount of water as all of Earth's oceans combined. These moons, along with Barnard's star, provide a tantalizing glimpse into the potential for habitability beyond Earth. But even as we uncover these extraordinary findings, a deeper mystery looms over the cosmos: the silence. This silence, often called the Fermi paradox, asks a deceptively simple question. If intelligent life is so probable, where is everyone? With billions of stars in the galaxy and even more planets likely orbiting them, why haven't we detected any signals, visited alien civilizations, or even seen evidence of their existence? To unravel this paradox, scientists have turned to frameworks like the Kardashev scale, which measures civilizations based on their ability to harness energy. A Type 1 civilization can utilize all the energy of its home planet. Humanity, by comparison, is barely a Type 0, using only a fraction of Earth's potential. A Type 2 civilization could harvest energy from its entire star system, while a Type 3 civilization would command the energy of an entire galaxy. If such advanced civilizations exist, or existed, why have they left no trace? Could it be that the universe itself contains a bottleneck, an insurmountable challenge that prevents most life from advancing beyond a certain point? This idea, known as the Great Filter, forces us to consider unsettling possibilities. Is the Great Filter behind us, meaning humanity is rare or even unique in overcoming it? Or does it lie ahead, suggesting a looming obstacle that most civilizations cannot survive? Despite these questions, humanity's search for life continues with relentless determination. We are now equipped with tools that past generations could only dream of. The James Webb Space Telescope, launched in 2021, is designed to peer into the atmospheres of distant planets, searching for the chemical fingerprints of life. The European Southern Observatory's espresso spectrograph, with its unmatched precision, is detecting the faint wobbles of stars caused by orbiting planets, enabling discoveries like Barnard B closer to home. Missions like NASA's Europa Clipper and the European Space Agency's JUICE mission are preparing to explore the icy moons of Jupiter. These missions will use radar, spectrometers, and cameras to study Europa and Ganymede in unprecedented detail, probing their icy crusts and oceans for signs of habitability. But this journey isn't just about technology. It's about philosophy, imagination, and the unyielding drive to understand. Each discovery raises profound questions. If we find life, microbial or intelligent, what would that mean for our understanding of existence? And if we don't, how would it change our perspective on Earth's uniqueness? The silence of the universe isn't a dead end. It's an invitation to explore. It challenges us to listen more carefully, to build better tools, and to expand our horizons. From the rocky landscapes of Barnard B to the icy depths of Europa, every step forward brings us closer to answering the ultimate question. Are we alone? This is the story we'll explore today. From the pioneering discovery of Barnard B to the geological wonders of Ganymede and Europa and the philosophical depths of the Fermi paradox, join us as we uncover the mysteries of the cosmos. What lies beyond our world? What secrets do these distant stars and moons hold? And what does it all mean for us? Get ready to journey across space and time to places where questions outnumber answers and possibilities stretch beyond imagination. Let's begin. Barnard Star Overview. When we think of the stars closest to Earth, names like Alpha Centauri or Proxima Centauri might come to mind. However, there's another star much less famous, but no less intriguing. Barnard Star. Located just 6 light-years away, it is one of the nearest stars to our solar system. While it doesn't shine brightly in our night sky, Barnard Star is a subject of great interest for astronomers, and its unique characteristics make it a key player in the search for exoplanets and the quest to understand the cosmos. Barnard Star resides in the constellation Ophiuchus, a region of the sky often associated with mystery and discovery. Unlike the Alpha Centauri system, which consists of multiple stars, Barnard Star stands alone, a solitary traveler in the vastness of space. Despite its proximity to Earth, this star is invisible to the naked eye, a testament to its dimness. So what makes Barnard Star so special? It belongs to a class of stars known as red dwarfs. These are the most common type of stars in the Milky Way galaxy, comprising roughly 70% of all stars. Red dwarfs are small, cool, and dim compared to stars like our Sun. Barnard Star, in particular, has only about 16% of the Sun's mass and emits less than 0.4% of the Sun's light. To put this in perspective, if the Sun were a blazing bonfire lighting up the sky, Barnard Star would be a faint, flickering ember struggling to illuminate its surroundings. This lack of brightness is why Barnard Star went unnoticed by ancient stargazers, and why even modern astronomers required specialized instruments to study it. Yet what it lacks in luminosity, it makes up for in uniqueness and significance. Barnard Star emits most of its energy in the infrared spectrum. Unlike the Sun, which radiates across a broad range of wavelengths, this star primarily shines in invisible infrared light. This characteristic is typical of red dwarfs and is a key reason why planets orbiting such stars often have unusual conditions. For a planet to receive as much energy as Earth does from the Sun, it would need to orbit much closer to a red dwarf like Barnard Star. But perhaps the most remarkable feature of Barnard Star is its motion. Stars in the night sky may appear stationary to us, but in reality they are constantly in motion. Barnard Star is no exception. In fact, it holds the title of the fastest moving star in our sky in terms of proper motion, which is the apparent motion of a star across the celestial sphere, as observed from Earth. Every year, Barnard Star moves more than 10 arc-seconds across the sky, roughly the width of a dime held at arm's length. This might not sound like much, but in astronomical terms, it's an extraordinary speed. Barnard Star's motion is so rapid that if you were to observe it over several decades, you would notice its position shifting against the backdrop of more distant stars. Why does Barnard Star move so quickly? The answer lies in its proximity and velocity. As one of the nearest stars to our solar system, Barnard Star is relatively close, which amplifies its apparent motion. Additionally, it is traveling at a remarkable speed of 56 kilometers per second relative to the Sun. That's over 200,000 kilometers per hour, a speed that could take you from New York to Los Angeles in less than a minute. This rapid motion is a result of Barnard Star's journey through the Milky Way galaxy. Like all stars, it is orbiting the galactic center, tracing a path influenced by gravity and the distribution of mass within the galaxy. Barnard Star's trajectory is unique, and its motion has been carefully tracked by astronomers for over a century. The story of its discovery dates back to 1916, when American astronomer Edward Emerson Barnard first measured its extraordinary proper motion. Using photographic plates to compare the star's position over time, Barnard noticed its rapid shift against the background stars. This discovery earned the star its name, and solidified its reputation as an object of scientific fascination. Interestingly, Barnard's star is not just moving quickly, it's also approaching our solar system. Current calculations suggest that it will continue to get closer over the next 10,000 years, reaching a minimum distance of about 3.75 light-years before slowly moving away again. This makes it a compelling target for future study, as it represents one of the most accessible stars for interstellar exploration. Despite its proximity and motion, Barnard's star has an unassuming nature. Its surface temperature is much cooler than the Sun's, at approximately 3,100 degrees Kelvin compared to the Sun's 5,778 degrees Kelvin. This cooler temperature contributes to its reddish hue, which gives red dwarfs their name. Barnard's star's low luminosity and small size are typical of red dwarfs, but these traits also make it a stable star. Unlike larger, hotter stars that burn through their fuel quickly and explode as supernovae, red dwarfs like Barnard's star burn their fuel slowly and steadily. This stability means that they can shine for tens of billions of years, far longer than the Sun's estimated lifespan. For astronomers, this longevity is significant because it provides a vast window of time for planets to form and evolve around red dwarfs. While Barnard's star itself is unlikely to host life as we know it due to its faint output and intense stellar activity, the discovery of planets around it, such as the recently confirmed Barnard B, adds to the growing list of exoplanets that challenge our assumptions about habitability. The proximity, dimness, and motion of Barnard's star make it an excellent laboratory for studying the dynamics of nearby stars. Its position allows astronomers to test cutting-edge techniques for detecting planets and studying stellar behavior. The discovery of Barnard B, a rocky planet orbiting this dim star, has reignited interest in red dwarfs as potential hosts for planetary systems. In addition to its scientific value, Barnard's star holds a unique place in the cultural imagination. It is a star that reminds us of the vastness of the cosmos and the smallness of our place within it. It whispers of mysteries yet to be uncovered and challenges us to look closer, think deeper, and reach further. As we continue to study Barnard's star, it serves as a beacon of curiosity and discovery. Its quiet presence in the night sky reminds us that even the faintest lights can guide us to profound truths about the universe. Barnard's star is more than just a star. It is a window into the possibilities that await us in the universe. Its proximity, motion, and unique characteristics make it a cornerstone of astronomical research, and its story is far from over. Join us as we explore the discoveries it has already inspired and the questions it continues to pose to humanity's quest for understanding. Early observations and planetary searches. The story of Barnard's star began in the early 20th century, a time when astronomers were just starting to unlock the secrets of the universe beyond our solar system. In 1916, the star captured the attention of Edward Emerson Barnard, a pioneering American astronomer whose keen eye and meticulous observations would cement its place in astronomical history. Edward Barnard was renowned for his exceptional ability to study faint celestial objects. Working with photographic plates, a cutting-edge technology of his time, he meticulously tracked the positions of stars, searching for unusual patterns or movements. It was during this work that he noticed something remarkable, a star that was moving faster across the sky than any other known star. This extraordinary motion earned the star its name, Barnard's star, and marked it as a prime candidate for further study. At the time of its discovery, Barnard's star was already notable for its proper motion. This apparent shift in position, caused by its proximity and velocity, was so significant that astronomers realized it was among the closest stars to our solar system. Its distance of just 6 light-years made it a fascinating subject, and its rapid motion suggested it was an intriguing traveler through our galactic neighborhood. But Barnard's star wasn't just interesting for its movement. Its proximity raised a tantalizing question. Could this unassuming red dwarf host planets? The possibility of planets orbiting nearby stars has always captivated astronomers, as such planets could provide invaluable insights into the nature of planetary systems, and perhaps even the potential for life beyond Earth. The first serious attempts to detect planets around Barnard's star began in the mid-20th century, By this time, astronomers had developed new techniques for studying stars, including astrometry, a method that measures the precise positions and movements of stars. Astrometry was seen as a promising way to detect planets, as the gravitational pull of an orbiting planet could cause a star to wobble slightly in its path. In the 1960s, using astrometric techniques, astronomers like Peter van de Kamp reported groundbreaking findings. Van de Kamp and his team believed they had detected a planet, or perhaps multiple planets, orbiting Barnard's star. These planets were thought to be large gas giants, similar in size to Jupiter or Saturn. The announcement generated excitement in the scientific community and beyond, as it seemed to confirm the presence of planets around one of our closest stellar neighbors. However, as often happens in science, the initial findings were met with skepticism. Over the following decades, astronomers attempted to replicate Van de Kamp's results using more refined methods and better equipment. These subsequent studies cast doubt on the existence of the proposed planets. It became clear that the wobbles detected in Barnard's star's motion were not caused by orbiting planets, but were instead artifacts of the observational techniques used at the time. Factors such as instrumental errors and imperfections in the photographic plates had introduced noise into the data, leading to false conclusions. By the 1980s, the idea of large planets around Barnard's star had been largely debunked. The initial excitement gave way to a more cautious approach, and astronomers began to rethink their strategies for detecting exoplanets. The failure to confirm planets around Barnard's star highlighted the limitations of astrometry and underscored the need for more reliable methods. The 1990s brought a new era in the search for exoplanets, thanks to the development of the radial velocity method. This technique revolutionized the field by allowing astronomers to detect planets indirectly through the subtle shifts in a star's light spectrum. As a planet orbits a star, its gravitational pull causes the star to move slightly toward and away from us. This motion creates tiny changes in the star's light. Red shifts when it moves away, and blue shifts when it moves toward us. These shifts can be measured with incredible precision, revealing the presence of orbiting planets. Radial velocity offered a major advantage over astrometry. While astrometry required precise measurements of a star's position, radial velocity relied on changes in light, which were easier to detect and less prone to errors. This method quickly became the gold standard for exoplanet detection and led to a wave of discoveries, including the first confirmed exoplanet orbiting a sun-like star in 1995. Barnard's star once again became a focus of attention. With its proximity to Earth and its status as a solitary red dwarf, it was an ideal candidate for radial velocity studies. Astronomers hoped that this new method would succeed where astrometry had failed, uncovering hidden planets around the star. Despite the promise of radial velocity, early attempts to detect planets around Barnard's star proved challenging. The star's small size and low luminosity made it difficult to observe, even with advanced instruments. Additionally, red dwarfs like Barnard's star are known for their stellar activity, including flares and magnetic variations, which can create false signals in the data. These challenges forced astronomers to refine their techniques further, developing more sensitive spectrographs capable of filtering out noise and isolating genuine planetary signals. In the late 2010s, a breakthrough finally occurred. Using cutting-edge spectrographs like the European Southern Observatory's HARPS instrument, astronomers detected a potential planet orbiting Barnard's star. This planet, designated Barnard B, was a rocky super-Earth located in a close orbit around the star. The discovery reignited interest in Barnard's star and demonstrated the power of radial velocity in revealing planets that had long eluded detection. The journey to uncover planets around Barnard's star has been a story of perseverance, innovation, and the relentless pursuit of knowledge. From the early days of astrometry to the modern era of radial velocity, each step has brought us closer to understanding this enigmatic star and its potential companions. Today, Barnard's star stands as a symbol of both the challenges and triumphs of exoplanet research. It reminds us that science is a process, a journey of discovery that requires patience, creativity, and the willingness to learn from our mistakes. The lessons learned from Barnard's star have shaped the field of astronomy and continue to inspire new generations of scientists as they explore the universe. The story of Barnard's star is far from over, As technology advances and our understanding deepens, this small red dwarf will undoubtedly continue to reveal its secrets. Breakthrough discovery. In the grand journey of scientific exploration, few moments are as thrilling as a breakthrough, when decades of curiosity and persistence finally yield answers. The story of Barnard's star is no exception. After years of speculation, technological advancements have allowed astronomers to uncover a remarkable discovery: the presence of a rocky planet orbiting this dim, fast-moving star. But this journey was far from straightforward. It is a story of false starts, unexpected challenges, and ultimately, a revolutionary breakthrough. In 2018, the astronomical community was abuzz with news that a potential super-Earth had been detected orbiting Barnard's star. This detection was made using some of the most advanced spectrographs available at the time, such as the HARPS and CARMENES instruments. These tools enabled astronomers to study the star's light with unparalleled precision, searching for the telltale wobble caused by the gravitational pull of an orbiting planet. This wobble, measured through the radial velocity method, revealed subtle shifts in the star's light spectrum. Red shifts as the star moved away from Earth, and blue shifts as it moved closer. These signals suggested the presence of a planet, designated as Barnard B, orbiting the star at a distance of approximately 0.4 astronomical units, or about 40% of the distance between the Earth and the Sun. This planet was intriguing for several reasons. First, its size was estimated to be slightly larger than Earth, classifying it as a super-Earth. Second, it was believed to have an orbital period of around 233 days. These characteristics raised exciting possibilities about its nature and the broader implications for planets around red dwarfs. While the surface conditions were deemed too harsh for life as we know it, temperatures were estimated to hover around -170 degrees Celsius due to the star's low luminosity. The discovery still represented a major milestone in exoplanet research. But science is rarely straightforward, and initial discoveries often require rigorous testing and reanalysis. In the years following the 2018 announcement, astronomers revisited the data with fresh eyes and more sophisticated analytical tools. By 2021, it became clear that the signals previously attributed to a planet might not be what they seemed. Upon closer examination, researchers found that the detected signals were likely caused by stellar activity rather than an orbiting planet. Red dwarfs like Barnard's star are known for their complex and dynamic behavior, including flares, magnetic cycles, and surface variability. These phenomena can create false positives in radial velocity data, mimicking the effects of an orbiting planet. The reanalysis in 2021 was a sobering moment for the astronomical community. It underscored the challenges of studying red dwarfs, whose faint light and turbulent activity make them both fascinating and difficult to observe. While the news was disappointing, it also highlighted the importance of advancing our techniques and developing even more precise instruments. The story took a dramatic turn in 2024. By this time, new advancements in technology had revolutionized exoplanet detection. Instruments like the European Southern Observatory's espresso spectrograph and the HARPS spectrograph had achieved levels of precision previously thought unattainable. These tools were designed to filter out the noise caused by stellar activity, isolating genuine planetary signals from the background variability of the star itself. With these state-of-the-art instruments, astronomers revisited Barnard's star, determined to settle the question once and for all. This time, their efforts paid off. In October 2024, the existence of Barnard B was confirmed beyond doubt. The data showed a consistent and measurable wobble in the star's motion, caused by the gravitational influence of a planet. Unlike earlier speculative attempts, this discovery was backed by a wealth of high-quality data and rigorous analysis. The measurements were precise, the methodology sound, and the results verified by independent teams worldwide. Barnard B was no longer a hypothetical entity, it was a confirmed planet, and its characteristics were more fascinating than ever. Barnard B is a super-Earth, slightly larger and more massive than our planet. It orbits its host star at an incredibly close distance, just 0.04 astronomical units, far closer than Mercury's orbit around the Sun. This proximity results in an orbital period of only 3 days, meaning a year on Barnard B passes in less than a week by Earth's calendar. The planet's surface conditions are extreme. Due to its close orbit and the nature of its host star, Barnard B is bombarded with intense radiation. Its surface temperatures are estimated to reach around 260 degrees Fahrenheit, creating an environment that is far too hostile for liquid water or life as we know it. While Barnard B itself is unlikely to host life, its discovery has profound implications for the study of exoplanets. First, it demonstrates that even faint dim stars like Barnard's star can harbor rocky planets. This finding challenges earlier assumptions that red dwarfs are unlikely hosts for such worlds. Second, the discovery highlights the potential for further exploration of the Barnard star system. Could there be additional planets, perhaps farther from the star and within the habitable zone? The tools and techniques used to confirm Barnard B could pave the way for uncovering more planets in the system and others like it. Finally, the story of Barnard B underscores the resilience and ingenuity of the scientific process. From the initial detection in 2018 to the rigorous reanalysis in 2021 and the eventual confirmation in 2024, this journey reflects the iterative nature of discovery. Each setback was met with renewed determination, and each challenge inspired innovative solutions. The confirmation of Barnard B is not just a triumph of technology, it is a testament to humanity's enduring curiosity and drive to explore the unknown. It reminds us that even the faintest lights in the universe can guide us to profound truths. As we look to the future, Barnard's star remains a beacon of possibility. Its proximity to Earth makes it an ideal target for further study, and its newly discovered planet offers a wealth of opportunities for research. With upcoming missions and advancements in observational technology, we may soon uncover even more secrets about this enigmatic star system. Barnard B is more than just a planet. It is a symbol of what we can achieve when science, perseverance, and imagination come together. As we continue to explore the cosmos, the story of Barnard's star serves as a reminder that the universe is vast, mysterious, and full of surprises waiting to be discovered. Characteristics of Barnard B. Barnard B, a rocky super-Earth orbiting one of our closest stellar neighbors, has become a subject of great fascination since its confirmation in 2024. This planet, while inhospitable for life as we know it, offers crucial insights into the nature of exoplanets around red dwarfs and the dynamics of planetary systems. To truly appreciate its significance, let's take a closer look at the characteristics that make Barnard B such an intriguing discovery. Barnard B orbits its host star at an astonishingly close distance of just 0.04 astronomical units. For context, an astronomical unit, or AU, is the average distance between the Earth and the Sun, about 93 million miles. By comparison, Mercury, the innermost planet in our solar system, orbits the Sun at 0.39 astronomical units, nearly 10 times farther away than Barnard B is from its star. This proximity places Barnard B in what is often called a tight orbit, a common feature of planets around red dwarfs. This extremely close orbit has a profound impact on the planet's environment. With such a short distance to its host star, Barnard B completes an orbit in just 3 days. Imagine that. A year on Barnard B is shorter than a single weekend on Earth. This rapid orbital period is a direct result of its proximity to Barnard's star, whose gravitational pull dominates the planet's motion. But this closeness comes at a cost. The intense radiation and heat from Barnard's star create extreme surface conditions on the planet. Temperatures on Barnard B are estimated to reach around 260 degrees Fahrenheit, hot enough to make water boil and far beyond the threshold for habitability as we understand it. These searing temperatures are compounded by the fact that red dwarfs, including Barnard's star, emit most of their energy in the infrared spectrum, further heating the planet's surface. Such conditions make it highly unlikely for liquid water to exist on Barnard B, a key requirement for life as we know it. The planet's atmosphere, if it exists, would likely be thin or non-existent due to the relentless bombardment of stellar radiation. Even if an atmosphere were present, it would be subjected to constant stripping by the star's activity, including flares and high-energy particles. Yet despite its harsh environment, Barnard B holds immense scientific significance. As a rocky super-Earth, it represents a category of planets that are slightly larger and more massive than our own. Understanding such planets is critical for broadening our knowledge of planetary formation and evolution, particularly in systems with red dwarf stars. Red dwarfs like Barnard's star are the most common type of star in the Milky Way, comprising roughly 70% of all stars. However, their low luminosity and frequent stellar activity had long led scientists to doubt their potential to host rocky planets. The discovery of Barnard B challenges these assumptions and suggests that rocky planets may be more common around red dwarfs than previously thought. Barnard B also serves as a stepping stone for exploring the broader potential of the Barnard star system. While this planet lies far too close to its star to be habitable, its discovery raises the tantalizing possibility of additional planets farther out. Could there be a world within the habitable zone of Barnard's star, where conditions might allow for liquid water and perhaps life? The habitable zone, often referred to as the Goldilocks zone, is the region around a star where temperatures are just right, not too hot, not too cold, for liquid water to exist on a planet's surface. For Barnard's star, this zone would be located farther out from the star, beyond the orbit of Barnard B. While no planets in this zone have been detected yet, the discovery of Barnard B proves that this system is capable of forming rocky planets, making it a promising target for future research. Studying Barnard B in detail, however, is not without its challenges. The star's faint light and the planet's close orbit make direct imaging difficult. Instead, astronomers rely on indirect methods, such as radial velocity and transit photometry to gather data. Instruments like the European Southern Observatory's espresso spectrograph have been crucial in confirming the planet's existence and measuring its characteristics. These tools provide valuable insights, but much about Barnard B remains unknown. For example, we have yet to determine its atmospheric composition, surface geology, or whether it has moons or magnetic fields. Answering these questions will require more advanced observational technologies, such as the James Webb Space Telescope or next-generation ground-based observatories. Despite these limitations, the discovery of Barnard B represents a monumental step forward in exoplanet research. It demonstrates that even faint, low-mass stars like Barnard's star can host rocky planets, expanding the range of environments where planets might exist. It also highlights the importance of red dwarfs as targets for future exploration, given their abundance and the variety of planetary systems they may harbor. Barnard B's characteristics also provide a valuable comparison to other exoplanets, particularly those around similar stars. For instance, Proxima Centauri b, another rocky planet orbiting a red dwarf, lies within its star's habitable zone. Comparing these two planets can help astronomers understand the factors that influence habitability and the role of stellar activity in shaping planetary environments. The discovery of Barnard B is not just about what we know, it's also about what we don't know. It raises new questions about the nature of planets around red dwarfs, the processes that govern their formation, and the possibility of finding more planets in the same system. As we continue to refine our methods and develop new technologies, Barnard B serves as a reminder of the vast potential for discovery in our cosmic backyard. Its proximity to Earth, just 6 light-years away, makes it an ideal candidate for future missions. While interstellar travel remains a distant dream, Barnard B could one day be studied in unprecedented detail by advanced telescopes or even robotic probes sent to its star system. Such missions would not only deepen our understanding of this particular planet, but also pave the way for exploring other nearby stars and their planets. Barnard B is more than just a rocky super-Earth in a tight orbit. It is a window into the complexities of planetary systems and the resilience of science. Its discovery marks a milestone in our journey to understand the universe, and it inspires us to keep asking questions, keep exploring, and keep reaching for the stars. As we continue to study this remarkable planet and its host star, one thing is clear: Barnard B is a small piece of a much larger puzzle, one that holds the potential to reshape our understanding of the cosmos and our place within it. Challenges of habitability in red dwarf systems. Red dwarf stars are among the most fascinating objects in the universe. They are the most common type of star in our galaxy, making up nearly 70% of all stars. Despite their abundance and potential to host planets, They present unique and often daunting challenges when it comes to supporting life. Stellar flares, tidal locking, and extreme conditions all complicate the picture. Yet these very challenges are what make red dwarf systems such intriguing subjects of study. Let's explore the difficulties of habitability around red dwarfs, the obstacles they present for life as we know it, and why, despite these challenges, they remain central to the search for habitable worlds. Red dwarfs are small, cool stars with relatively low energy output. Their diminutive size and dim light mean that any planet seeking conditions similar to Earth's must orbit very close to the star to receive enough warmth. This proximity, however, creates its own set of problems. The first major challenge is the issue of stellar flares. Unlike our Sun, which has periods of calm interspersed with solar storms, red dwarfs are notoriously volatile. They frequently produce powerful flares, eruptions of high-energy radiation that can dramatically affect nearby planets. These flares release bursts of ultraviolet, UV, and X-ray radiation that are hundreds, even thousands, of times more intense than those from the Sun. For planets orbiting close to red dwarfs, this radiation can be devastating. A single stellar flare can strip away a planet's atmosphere, leaving it exposed to the harsh conditions of space. Without an atmosphere to protect it, the planet becomes a barren, lifeless world. Even if the planet begins with an Earth-like atmosphere, repeated exposure to such flares can erode it over time, making the long-term retention of an atmosphere extremely difficult. One notable example of this phenomenon is Proxima Centauri b, a planet orbiting the closest star to our solar system. While it lies within its star's habitable zone, Proxima Centauri is an active red dwarf that frequently emits powerful flares. These flares are strong enough to strip the planet's atmosphere or prevent it from forming in the first place. Studies of Proxima b have revealed that the conditions for life are far more hostile than initially imagined, despite the planet's favorable location. The second major challenge facing planets around red dwarfs is tidal locking. Tidal locking occurs when a planet's rotation period becomes synchronized with its orbital period. This means that one side of the planet always faces the star, while the other side is perpetually in darkness. This phenomenon is common in red dwarf systems due to the close proximity of their planets. The gravitational forces between the star and the planet create tidal effects that gradually slow the planet's rotation until it becomes tidally locked. The consequences of tidal locking are dramatic. The side of the planet facing the star becomes scorching hot, bathed in constant light and heat. Meanwhile, the dark side of the planet plunges into frigid cold, never receiving any warmth from the star. This creates an extreme temperature contrast between the two hemispheres, with one side resembling a scorching desert and the other an icy wasteland. For life to exist on a tidally locked planet, it would have to thrive in the narrow terminator zone, the region between the day side and the night side where temperatures might be more moderate. However, even this zone is fraught with challenges. Winds generated by the extreme temperature differences can create turbulent weather patterns, making the environment unpredictable and potentially uninhabitable. Additionally, tidal locking affects more than just the surface conditions. The lack of rotation means that the planet's magnetic field may weaken or fail entirely. A strong magnetic field is essential for protecting a planet's atmosphere from stellar radiation. Without it, the atmosphere can be stripped away, as we see with Mars in our own solar system, which has a weak magnetic field and a thin atmosphere. Despite these formidable challenges, red dwarf systems continue to surprise scientists. Over the past decade, some of the most exciting discoveries in exoplanet research have come from planets orbiting red dwarfs. For example, the TRAPPIST-1 system, located about 39 light-years away, hosts 7 Earth-sized planets, 3 of which lie within the habitable zone. This discovery was groundbreaking because it demonstrated that red dwarfs could host not just one, but multiple potentially habitable planets. Similarly, discoveries like LHS 1140b and Proxima Centauri b have shown that rocky planets around red dwarfs are not only common, but also diverse. These planets vary in size, composition, and orbital characteristics, suggesting that red dwarfs may be fertile grounds for planetary systems. So how do these planets manage to defy the odds? One possibility is that some planets around red dwarfs have mechanisms to protect their atmospheres. For example, A strong magnetic field could shield the planet from stellar flares, preventing atmospheric loss. Another possibility is that these planets might have atmospheres composed of heavy molecules, such as carbon dioxide, which are harder to strip away. Additionally, some red dwarfs are less active than others. While many exhibit frequent flaring, some, like Barnard's star, are relatively stable. Planets orbiting quieter red dwarfs may have a better chance of retaining their atmospheres and supporting life. Despite these promising discoveries, the search for life around red dwarfs remains challenging. The unique conditions of these systems require innovative approaches to study them. Instruments like the James Webb Space Telescope are expected to play a crucial role in this endeavor. By analyzing the atmospheres of exoplanets in red dwarf systems, scientists hope to determine whether these planets have the necessary ingredients for life, such as water, oxygen, and other biosignatures. Moreover, the sheer abundance of red dwarfs makes them invaluable targets for future exploration. With billions of red dwarfs in our galaxy, even a small percentage hosting habitable planets would mean countless worlds with the potential for life. The challenges of habitability in red dwarf systems are undeniable, but they also represent an opportunity. By studying these unique environments, we can expand our understanding of what makes a planet habitable and redefine the boundaries of where life might exist. Red dwarfs, with their quirks and complexities, remind us that the universe is vast and full of surprises. As we continue to explore these systems, we may one day find a planet that not only survives the challenges of its red dwarf host, but thrives despite them. Such a discovery would be a testament to the resilience of life and the boundless potential of the cosmos. The story of red dwarfs and their planets is far from over. These small but mighty stars hold the key to some of the greatest mysteries of the universe, and their challenges only make the journey more compelling. Join us as we uncover more about these fascinating systems and the secrets they may hold. The broader implications. The discovery of planets around nearby stars like Barnard's star is not just about finding new worlds. It's about advancing our understanding of the universe and pushing the boundaries of science. Each new finding serves as a stepping stone, leading to breakthroughs in exoplanet research, technological innovation, and our quest to answer the age-old question, are we alone in the cosmos? At the heart of this revolution in exoplanet research is the relentless pursuit of better tools and technologies. Instruments like the European Southern Observatory's espresso spectrograph and the James Webb Space Telescope are redefining what we can achieve in the study of distant worlds. These advancements are not only unveiling the secrets of stars like Barnard's star, but are also laying the groundwork for future discoveries that could change our understanding of life in the universe. Let's begin with espresso, a cutting-edge spectrograph that has become a cornerstone of modern astronomy. Short for Eschel spectrograph for rocky exoplanet and stable spectroscopic observations, espresso is designed to detect the faintest signals from stars, enabling astronomers to identify the presence of orbiting planets. What sets espresso apart is its unparalleled precision. Unlike earlier instruments, which struggled to filter out the noise caused by a star's natural activity, espresso can measure tiny shifts in a star's light spectrum with extraordinary accuracy. These shifts, caused by the gravitational pull of an orbiting planet, are what astronomers rely on to detect exoplanets using the radial velocity method. For Barnard's star, espresso was a game changer. The star's faint light and turbulent activity had long made it a challenging target, but espresso's precision allowed astronomers to isolate genuine planetary signals from background noise. It was with this instrument that the existence of Barnard B was confirmed, marking a major milestone in the study of nearby exoplanets. While espresso excels at detecting planets and measuring their masses, the James Webb Space Telescope, or JWST, is poised to revolutionize our understanding of their atmospheres. Launched in 2021, JWST is the most advanced space telescope ever built. Its primary mission is to study the universe in infrared light, a capability that makes it uniquely suited for examining the atmospheres of distant planets, including those around red dwarfs like Barnard's star. One of JWST's greatest strengths is its ability to perform transit spectroscopy. This technique involves analyzing the light from a star as it passes through a planet's atmosphere during a transit. By studying how the starlight is absorbed at different wavelengths, astronomers can determine the composition of the planet's atmosphere, identifying molecules like water vapor, carbon dioxide, and methane, all potential indicators of life. For Barnard B, JWST represents an exciting opportunity. While the planet's extreme proximity to its star makes it unlikely to host life, understanding its atmospheric composition could provide valuable insights into the conditions around red dwarfs. Additionally, JWST's observations could help identify other planets in the Barnard star system, particularly those farther out, in the habitable zone where liquid water might exist. The broader implications of these technologies extend far beyond Barnard's star. Instruments like ESPRESSO and JWST are enabling astronomers to study exoplanets with a level of detail that was unimaginable just a decade ago. This newfound precision is allowing us to explore fundamental questions about planetary formation, atmospheric chemistry, and the potential for life beyond Earth. Barnard's star, in particular, has emerged as a prime candidate for ongoing research. Its proximity to Earth, just 6 light-years away, makes it an accessible target for advanced telescopes and observational campaigns. Moreover, its status as a solitary red dwarf with a confirmed rocky planet provides a unique laboratory for studying the dynamics of such systems. The discovery of Barnard B has sparked renewed interest in the star, prompting scientists to ask, could there be more planets waiting to be found? Red dwarf systems are known for their compact arrangements, with multiple planets often orbiting close to their stars. If Barnard's star follows this pattern, it's possible that additional worlds, including those in the habitable zone, remain undetected. Future missions and instruments are expected to play a key role in this search. The upcoming Extremely Large Telescope, ELT, currently under construction in Chile, will be equipped with powerful instruments capable of directly imaging exoplanets. With its massive 39-meter mirror, the ELT will be able to capture detailed images of nearby star systems, providing a clearer picture of Barnard's star and its potential planetary companions. But the implications of studying Barnard's star go beyond the search for planets. It also serves as a testing ground for refining our methods and pushing the limits of technology. For example, the challenges of observing a faint, active red dwarf have driven advancements in spectrograph design, data analysis techniques, and atmospheric modeling. These innovations are not only enhancing our understanding of Barnard's star, but are also being applied to the study of other stars and systems across the galaxy. The lessons learned from Barnard's star are helping scientists address some of the most profound questions in astronomy. How do planets form around red dwarfs? And why are rocky planets like Barnard B so common in these systems? What factors determine whether a planet can retain its atmosphere in the face of stellar flares and radiation? And most importantly, where should we look next in our search for life? The answers to these questions could reshape our understanding of the universe. By studying stars like Barnard's star, we are expanding the boundaries of habitability and challenging our assumptions about what it means for a planet to be Earth-like. The discovery of rocky planets around red dwarfs suggests that the conditions for life might be far more diverse than we ever imagined, opening up new possibilities for where we might find it. As we continue to explore Barnard's star and its planetary system, the potential for discovery is limitless. Each new observation brings us closer to understanding the nature of these distant worlds and our place in the cosmos. Whether it's through ESPRESSO's precision measurements, JWST's atmospheric studies, or the unprecedented capabilities of the ELT, the tools of modern astronomy are bringing the universe into sharper focus. And Barnard's star, with its rocky companion and proximity to Earth, remains a shining example of what we can achieve when science, technology, and curiosity come together. It is a reminder that the universe is vast, mysterious, and full of surprises waiting to be uncovered. The story of Barnard's star is far from over. Its secrets continue to inspire scientists and fuel our quest for knowledge. As we look to the future, one thing is certain: the discoveries we make around this unassuming red dwarf will echo across the field of astronomy, guiding us toward new horizons and deeper understanding. Expanding the search for life. The search for life beyond Earth is one of humanity's most profound endeavors. It challenges us to confront our place in the cosmos, to ponder the possibilities of civilizations far more advanced than our own, and to grapple with the unsettling silence that stretches across the vastness of space. To frame this search, scientists have developed concepts like the Kardashev scale, the Great Filter, and the Fermi paradox, tools that help us navigate the mysteries of the universe and refine our approach to detecting life and intelligence among the stars. At the heart of this exploration is the Kardashev scale, a theoretical framework proposed by Soviet astronomer Nikolai Kardashev in 1964. The scale categorizes civilizations based on their ability to harness and utilize energy. It begins with Type 1 civilizations, which can harness all the energy available on their home planet. Earth, by comparison, is currently at about 0.73 on the Kardashev scale, still working toward full utilization of planetary energy. Moving up the scale, Type 2 civilizations are capable of capturing all the energy of their host star. This level of advancement might involve the construction of megastructures like a Dyson sphere, a hypothetical system that could surround a star and capture its energy output. A Type 3 civilization goes even further, harnessing energy on the scale of an entire galaxy. Such a civilization would likely possess technology far beyond our comprehension, potentially altering or even controlling the physical structures of the universe itself. But why haven't we found evidence of these advanced civilizations? The Kardashev scale highlights the immense energy and resources required to achieve each level, but it also raises a critical question: is there something preventing civilizations from reaching these heights? This is where the concept of the Great Filter comes into play. The Great Filter suggests that there may be a universal bottleneck, an obstacle so difficult to overcome that most, if not all, civilizations fail before reaching the point of interstellar communication or colonization. This filter could occur at various stages. It might be the emergence of life itself, the development of intelligent beings, or the survival of advanced civilizations in the face of existential threats like nuclear war, climate change, or artificial intelligence. If the Great Filter lies behind us, it would mean that humanity has already overcome the most significant barriers to advanced civilization, making us a rare or even unique species in the galaxy. But if the filter lies ahead, the silence we observe in the universe might be a warning, a sign that most civilizations self-destruct before achieving Type 1 status on the Kardashev scale. The apparent absence of extraterrestrial civilizations brings us to the Fermi paradox, named after physicist Enrico Fermi. During a casual conversation with colleagues in 1950, Fermi famously asked, "Where is everybody?" His question captures the contradiction between the high probability of intelligent life in the universe and the lack of evidence for its existence. The Fermi paradox forces us to confront the eerie silence of the cosmos. If life is common as the sheer number of stars and planets would suggest, why haven't we detected it? Why haven't advanced civilizations visited or contacted us? There are several possible explanations for the Fermi paradox. One is that intelligent life is exceedingly rare, either because the conditions for its emergence are unique or because the Great Filter prevents most civilizations from advancing. Another possibility is that advanced civilizations exist but choose not to communicate, either because they see no benefit or because they adhere to a principle like the cosmic zoo hypothesis. The idea that Earth is being observed but deliberately left undisturbed, much like a wildlife preserve. It's also possible that we simply lack the tools or understanding to recognize signs of extraterrestrial intelligence. Civilizations more advanced than ours might communicate using technologies or wavelengths that we cannot yet detect. Alternatively, their methods of communication might be so alien that we fail to recognize them as deliberate signals. Despite the silence, humanity remains determined to search for signs of life. One of the key tools in this endeavor is the Search for Extraterrestrial Intelligence, or SETI, a global scientific initiative that scans the skies for artificial radio signals. For decades, SETI has used powerful radio telescopes to listen for transmissions from distant stars, focusing on the frequencies where natural cosmic noise is minimal. While SETI has yet to find definitive evidence of extraterrestrial intelligence, the search is far from over. Advances in technology, such as machine learning and artificial intelligence, are enabling researchers to analyze vast amounts of data more efficiently, increasing the chances of identifying faint or complex signals that might otherwise go unnoticed. In addition to listening for signals, scientists are also exploring the potential for biosignatures and technosignatures, observable characteristics that might indicate the presence of life or advanced civilizations. Biosignatures include atmospheric molecules like oxygen, methane, and water vapor, while technosignatures encompass phenomena like artificial light, industrial pollution, or the detection of megastructures like Dyson spheres. The James Webb Space Telescope, with its ability to analyze the atmospheres of exoplanets, represents a significant leap forward in this search. By studying the chemical compositions of distant worlds, JWST could provide crucial clues about the presence of life, even on planets orbiting faint stars like Barnard's star. But what if we never find evidence of intelligent life? What if the silence persists? For some, this would be a sobering realization, underscoring the uniqueness and fragility of life on Earth. For others, it would serve as a call to action, a reminder that humanity must take responsibility for its future and ensure its survival in a universe that may be devoid of other voices. The Fermi paradox, the Kardashev scale, and the Great Filter all challenge us to think deeply about the nature of existence and the limits of human understanding. They remind us that the search for life is not just a scientific endeavor, but a philosophical one, forcing us to confront our assumptions, aspirations, and fears about the cosmos. As we expand our search for life, we are also expanding the boundaries of what we know and what we can imagine. Whether through the discovery of microbial life on a distant exoplanet or the detection of an advanced civilization light years away, each step brings us closer to answering the most profound questions of all. Are we alone? And if we are not, what does it mean to share the universe with others? The search for life is more than a quest for discovery. It is a journey of self-reflection and growth. It challenges us to push the limits of our knowledge, to innovate, and to dream. As we continue this journey, the silence of the universe will not deter us. Instead, it will inspire us to listen more carefully, to look more deeply, and to explore more boldly than ever before. Case study: Ganymede. Among the countless celestial bodies in our solar system, few are as intriguing as Ganymede, one of Jupiter's many moons. This extraordinary satellite is a world of superlatives. It is the largest moon in the solar system, even surpassing the planet Mercury in size. But Ganymede's appeal extends far beyond its sheer dimensions. It boasts unique features that set it apart from every other moon: a magnetic field, a subsurface ocean, and a surface marked by a complex geological history. Over the years, missions like Galileo and Juno have unveiled the mysteries of Ganymede, painting a picture of a moon that is not only scientifically fascinating, but also a potential candidate in the search for extraterrestrial life. Let's dive into the story of Ganymede, a world that challenges our understanding of moons and planets alike. Ganymede was first observed in 1610 by Galileo Galilei, along with 3 other Jovian moons, Io, Europa, and Callisto. These discoveries were groundbreaking at the time, providing the first evidence that celestial bodies could orbit something other than Earth, challenging the geocentric view of the universe. But Ganymede quickly stood out from its siblings, thanks to its immense size. With a diameter of approximately 5,268 kilometers, 3,273 miles, Ganymede is not just the largest moon in the solar system, it's larger than the planet Mercury. If Ganymede orbited the Sun instead of Jupiter, it might even qualify as a planet in its own right. Size, however, is only the beginning of Ganymede's story. What truly makes this moon extraordinary are its unique physical and magnetic characteristics. Unlike any other moon, Ganymede generates its own magnetic field. This magnetic field, first detected by NASA's Galileo spacecraft in the 1990s, is thought to be produced by a liquid iron or iron-nickel core, much like Earth's. The presence of a magnetic field has significant implications for Ganymede's environment. It creates a magnetosphere, a protective bubble around the moon, that interacts with Jupiter's powerful magnetosphere, resulting in complex and dynamic electromagnetic phenomena. For example, this interaction generates auroras in Ganymede's thin atmosphere, a stunning visual display that provides valuable clues about the moon's composition and internal structure. One of the most exciting revelations about Ganymede is the evidence for a subsurface ocean. Beneath its icy crust lies a vast body of liquid water, potentially containing more water than all of Earth's oceans combined. This ocean, sandwiched between layers of ice, is kept liquid by heat generated from tidal forces exerted by Jupiter and its other moons. The discovery of this ocean has transformed Ganymede from a frozen, lifeless world to a tantalizing candidate in the search for life beyond Earth. On our own planet, wherever there is water, there is life. While the conditions on Ganymede are far harsher, the presence of liquid water raises the possibility of microbial life, especially near hydrothermal vents that could exist on the ocean floor. Our understanding of Ganymede has been shaped by decades of exploration, particularly by missions like Galileo and Juno. The Galileo spacecraft, launched by NASA in 1989, was the first to make detailed observations of Ganymede. During its 8-year mission in the Jovian system, Galileo conducted multiple flybys of the Moon, capturing high-resolution images of its surface, measuring its magnetic field, and detecting the subsurface ocean. Galileo's findings revolutionized our understanding of Ganymede. Its images revealed a surface with two distinct types of terrain: dark, heavily cratered regions that date back billions of years, and lighter, grooved regions that suggest more recent geological activity. These grooves, some stretching for hundreds of miles, indicate that Ganymede's icy crust has been shaped by tectonic forces, an unexpected discovery for a moon so far from the sun. More recently, NASA's Juno spacecraft, launched in 2011, has provided new insights into Ganymede. While Juno's primary mission is to study Jupiter, it has made several close flybys of its moons, including Ganymede. In June 2021, Juno passed just 645 miles, 1,038 kilometers, above Ganymede's surface, capturing some of the most detailed images of the moon to date. These images reveal a complex, icy landscape marked by craters, grooves, and ridges. Juno's data also confirm variations in the composition of Ganymede's surface ice, providing clues about the processes that have shaped the moon over billions of years. The geology of Ganymede is a window into its dynamic past. The dark regions on its surface are thought to be ancient, dating back nearly 4 billion years. They are heavily cratered, indicating a long history of impacts. In contrast, the lighter regions are much younger and feature intricate patterns of ridges and grooves. These features are believed to result from tectonic forces, where the icy crust stretches and fractures due to internal pressures. This process creates faults and ridges, much like tectonic activity on Earth, but in a much colder and more alien environment. The presence of liquid water beneath Ganymede's surface raises profound questions about its potential for habitability. While the moon's surface is far too cold and exposed to radiation for life to survive, its subsurface ocean could offer a more hospitable environment. On Earth, life thrives in extreme environments, from deep-sea hydrothermal vents to subglacial lakes in Antarctica. These ecosystems rely on chemical energy rather than sunlight, suggesting that similar life forms could exist on Ganymede if the right conditions are present. But habitability depends on more than just water. Scientists are also interested in the composition of Ganymede's ocean. Is it salty, like Earth's oceans? Does it contain the necessary chemical ingredients for life, such as carbon, nitrogen, and phosphorus? These questions remain unanswered, but future missions could provide the data needed to explore them. The next chapter in Ganymede's exploration will be written by the European Space Agency's JUICE mission, the Jupiter Icy Moons Explorer. Scheduled to arrive in the Jovian system in the 2030s, JUICE will conduct detailed studies of Ganymede, Europa, and Callisto. Equipped with advanced instruments, JUICE will map Ganymede's surface, analyze its magnetic field, and probe its subsurface ocean. NASA's upcoming Europa Clipper mission could also contribute indirectly to our understanding of Ganymede. While focused on Europa, Clipper's findings about icy moon environments could provide valuable context for interpreting Ganymede's data. Studying Ganymede is about more than understanding a single moon. It's about expanding our knowledge of the solar system and the possibilities for life. Ganymede's unique combination of size, magnetic field, and subsurface ocean makes it a natural laboratory for studying planetary processes and the conditions that might support life. It also provides a valuable comparison to other icy worlds, such as Europa and Saturn's moon Enceladus, both of which are considered prime candidates for habitability. By studying these moons together, scientists can identify commonalities and differences, helping to refine our search for life beyond Earth. Ganymede reminds us that the solar system is a place of endless surprises. From its magnetic field to its hidden ocean, this moon challenges our assumptions and expands our horizons. It is a testament to the power of exploration and a reminder that even the coldest, most distant worlds can hold the keys to understanding life's potential in the universe. As we look to the future, Ganymede stands as a symbol of what we have discovered and what we have yet to learn. It is a reminder that the journey of exploration is far from over, and that the answers we seek may be closer than we think, waiting just beneath the icy surface of a moon orbiting Jupiter. Case study: Europa. Among the celestial bodies of our solar system, Jupiter's moon, Europa stands out as one of the most promising candidates in the search for extraterrestrial life. Beneath its thick, icy crust lies a secret that has captivated scientists for decades: a vast, subsurface ocean containing more water than all of Earth's oceans combined. Europa's unique characteristics, its ice ridges, salt deposits, and geysers, have painted a tantalizing picture of a world that could potentially harbor life. Let's embark on a journey to explore Europa, an icy moon that holds the promise of answers to some of humanity's most profound questions. Europa, discovered in 1610 by Galileo Galilei, is one of the 4 Galilean moons of Jupiter. With a diameter of about 3,121 kilometers, 1,940 miles, it is slightly smaller than Earth's moon. Yet what Europa lacks in size, it makes up for in scientific intrigue. At first glance, Europa's surface appears deceptively simple, a smooth, icy shell with relatively few craters. However, this simplicity belies a dynamic and complex environment. The surface is crisscrossed with reddish-brown streaks and ridges, features that have become key indicators of the moon's underlying secrets. One of Europa's most compelling characteristics is its subsurface ocean, which lies beneath an ice crust estimated to be 15 to 25 kilometers, 10 to 15 miles thick. This ocean, kept liquid by heat generated through tidal forces exerted by Jupiter's immense gravity, could be as deep as 100 kilometers, 62 miles. If these estimates are correct, Europa's ocean could contain more than twice the amount of water found on Earth, making it one of the largest reservoirs of liquid water in the solar system. Water is a fundamental ingredient for life as we know it, and Europa's vast ocean raises tantalizing questions about its potential habitability. Could this hidden ocean provide the conditions necessary for life to emerge and thrive? Europa's surface offers several clues about what lies beneath. The moon's ice ridges and chaotic terrain suggest that its crust is not static but dynamic, shaped by the movement of the subsurface ocean. These ridges, some of which span hundreds of miles, are thought to form as liquid water or slushy ice from below rises through cracks in the surface, freezing and creating the distinctive patterns observed by spacecraft. Another key feature of Europa's surface is the presence of salt deposits, which give the icy crust its reddish-brown coloration. These deposits, detected by instruments on spacecraft like Galileo, provide strong evidence that material from the subsurface ocean is being transported to the surface. The composition of these salts, which includes magnesium sulfate and other compounds, suggests a chemically rich environment that could potentially support life. Adding to Europa's intrigue are the geysers of water vapor that have been observed erupting from its surface. First detected by the Hubble Space Telescope in 2012, these plumes shoot water vapor hundreds of kilometers into space, creating an opportunity to sample the moon's subsurface ocean without drilling through its thick crust. These geysers are thought to result from pockets of water within the ice that are pressurized and released through cracks or vents. The presence of such plumes has sparked excitement among scientists, as they provide a direct window into the ocean below and offer a chance to study its composition. Our understanding of Europa has been shaped by several space missions, particularly NASA's Galileo spacecraft. Launched in 1989, Galileo spent 8 years in the Jovian system, conducting multiple flybys of Europa. Its instruments provided valuable data about the moon's surface, magnetic field, and potential subsurface ocean. One of Galileo's most important discoveries was the detection of an induced magnetic field around Europa, a strong indicator of a conductive layer beneath the surface, most likely a salty ocean. This finding confirmed that Europa was not just an icy moon, but a dynamic world with the potential to harbor life. While Galileo laid the foundation, future missions will take Europa exploration to new heights. NASA's Europa Clipper, set to launch in 2024, is designed specifically to investigate the moon's habitability. Equipped with a suite of advanced instruments, Europa Clipper will conduct detailed flybys of the moon, mapping its surface, analyzing its ice shell, and studying its subsurface ocean. Europa Clipper will use radar to penetrate the ice and determine the thickness of the crust, as well as the depth and salinity of the ocean. Spectrometers will analyze the composition of the surface and plumes, searching for organic molecules and other signs of habitability. High-resolution cameras will capture detailed images of Europa's terrain, identifying regions of interest for future exploration. One of the mission's primary goals is to assess whether Europa's ocean has the conditions necessary for life. This includes studying the availability of energy sources, such as hydrothermal vents, which could provide the heat and nutrients needed to sustain life. Europa Clipper is just the beginning. Scientists are already envisioning even more ambitious missions, including landers and subsurface probes that could directly sample the ocean. These missions would face significant technical challenges, such as drilling through miles of ice and surviving Europa's harsh radiation environment. However, the potential rewards, discovering life on another world, make these challenges worth pursuing. Europa's study is not just about understanding one moon. It's about answering fundamental questions about the nature of life in the universe. If life exists in Europa's ocean, it would suggest that life is not unique to Earth, but a natural outcome of the right conditions. Such a discovery would have profound implications for our understanding of biology, evolution, and our place in the cosmos. Even if Europa proves to be lifeless, its study will still provide valuable insights into the processes that shape icy worlds. By comparing Europa to other moons, such as Ganymede and Enceladus, scientists can refine their models of planetary formation and habitability, guiding future exploration efforts. Europa reminds us that the solar system is full of surprises, and that the search for life is not limited to Earth-like planets around distant stars. This icy moon, orbiting a giant planet in the cold outer reaches of the solar system, challenges our assumptions about where life can exist and what it means to be habitable. As we prepare for Europa Clipper and beyond, the excitement of discovery continues to grow. Whether we find life or uncover new mysteries, Europa's exploration is a testament to humanity's enduring curiosity and determination to understand the universe. Europa is more than just a moon. It is a symbol of the unknown, a reminder that the answers to some of our greatest questions may lie hidden beneath the ice of a distant world. As we look to the future, we can only imagine what secrets Europa will reveal and how they will reshape our understanding of life, the solar system, and the universe itself. Closing thoughts: humanity's journey to understand the cosmos is as vast as the universe itself. From the first telescopic observations by Galileo to the advanced missions probing distant worlds today, our relentless curiosity drives us to explore, question, and discover. Each new breakthrough, whether it's the detection of an exoplanet or the study of an icy moon, brings us closer to understanding the intricate tapestry of the cosmos and our place within it. But this quest is far from over. To uncover the secrets of the universe, we must continue to push the boundaries of technology and innovation. Instruments like the James Webb Space Telescope and missions like Europa Clipper and JUICE are just the beginning. Future advancements will need to go even further, developing more sensitive detectors, faster spacecraft, and autonomous systems capable of exploring the most inhospitable environments in our solar system and beyond. As we stand on the cusp of potentially discovering extraterrestrial life, we are faced with profound questions. What would it mean to know we are not alone? How would such a discovery reshape our understanding of ourselves, our origins, and our future? The silence of the universe invites us to listen more carefully, to look more deeply, and to continue searching. Because ultimately, the journey to explore the cosmos is not just about what we might find, it is about the endless possibilities that lie ahead.